Hey everyone, it's Miss Krupstedt here, and this lesson is going to be covering a section that we call 10.0, and we call it 0 because it doesn't actually have a section number in our curriculum, the Savas curriculum. However, it is something that starts getting mentioned and used throughout this chapter, and it has really helped in the past to have an entire day that goes over this notation, because otherwise they just sort of tell you, hey, start using it, and you don't know what it means. This notation is just a different way to express something we've already seen, which is an inequality. So an inequality are these little Pac-Man symbols or alligator symbols, some people call them. They are these four that I have here, but there's more than this. But we'll talk about what these mean. This one we would say less than. And if these are things that you forget, you mix them up, you might consider writing this on your note sheet somewhere so that you remember how to read these out loud. So this would be x is less than 4. Here's also the less than. This one is different. It's still less than, but that little line underneath it means it could be equal to. And then this one is greater than. And because it has the equals or the line underneath, it could be or equal to. There's also just the regular greater than symbol if you're looking for all of them. Now, what inequalities do is they allow us to express infinite solutions without having to write all infinite solutions. So what I mean by that is if I, in this first one, am saying x is less than 4, well, there's a lot of numbers that are less than 4. And if I was trying to list out all the answers, there's no way I could do that. I'd be here all day. So the answers would be 3, 2, 1, even something like 3.9 would work because it's technically less than 4. Okay. In the second one, this is called a compound inequality because it has two numbers. This is basically saying that x has to be between 0 and 10, but it cannot equal 0. So that could be 0.0000001, and that would count. It could also be anything up to 10. And then x is greater than or equal to -3. It could be -3, -2, -1. It could be 5,275,000. Okay, anything greater than -3. And again, these allow us to make things simpler when we're writing infinite solutions. We're going to make it even simpler, though, by introducing something called interval notation. I'm going to show you what it looks like on the next screen. All right, so here we have a number line, right? Hopefully you've seen these open and closed dots before. An open dot means we can be equal to that value, and a closed dot means we cannot be equal to that number. Okay, so in these two number lines, I started with something a little bit simpler. We have this compound inequality where we have the -5, change my color here, this -5, which corresponds to that -5. We have this it's technically less than or equal to, so we have that closed dot, so we have an equal to line underneath. Then we have has to be less than 4, where this less than symbol correlates to that open dot. This works, right? It expresses it could be anything between -5 and 4, and it could equal -5. But sometimes we get confused with the inequality symbols and the directions that they have to go. So today, again, we're going to introduce interval notation. Interval notation, if you look at it, it looks a lot like an ordered pair, like a point, except for we have some different symbols used. With the parentheses, we also have brackets. And what I hope you can kind of notice is that this bracket correlates to that inequality that has the line underneath it. Similar to this one, we had a less than or equal to line next to -9, and we have a bracket there. That bracket is just representing that we could equal that number. And then it has to be between those two values. So it has to be between -5 and +4. Okay, so it's a really slick way of writing it because you only need to know those two values and you don't have to worry about those alligator symbols. Let's look at a couple more that are a little bit more confusing. All right, here we have inequalities that aren't between values. They keep going on and on and on forever in a direction. So here we have -3, and notice we have that line underneath the inequality because it could equal it. And we have the fact that it could be anything bigger than -3. So that's what that says. X has to be greater than or equal to -3. Fun fact, when you're doing inequalities and you have arrows, your inequality will always match the direction of your arrow. If you didn't know that trick, I'm glad I could share that with you. Now, with the interval notation, it is a little bit different because, again, it looks like a point. So we have the -3, and we have that bracket, which means it could be equal to, but now we have this infinity thrown in. Why do you think we have infinity over there? Well, it has to do with the fact that we always need two values in interval notation. We need the smallest that it could be, and we need the biggest that it could be. So the smallest is -3, and the biggest that it could possibly be is infinity. And then we have the regular parentheses there because, and we'll write this down in our note sheet, you can never equal infinity. Even if you wanted to try, you would never get there. The second you touched infinity or equaled it, it would keep going. So you will always have a regular parenthesis next to infinity. Okay, similar to in the second one, we have a less than because we have an open dot and our arrow is pointing to the left or to all the numbers that are smaller than 1 and we're not equal to it. Now here you'll notice that the number is on the right side in our inequality or interval notation, and that's because 1 is technically the biggest that it could be. In this previous one, infinity was the biggest that we could be, but in this one, 1 is the biggest. We have a regular parenthesis because it can't equal 1, and then the smallest that it could be is negative infinity because it keeps going negative, and we use a regular parenthesis. All right, let's write some of this down in our notes. Interval, interval notation. All right, the first thing that we want you to know is that there are two, it looks like a point, but there are two types of symbols you can put around what looks like a point. It's not a point, but it looks like one. You could use brackets, and those brackets would represent something like it's less than or equal to or greater than or equal to. It is a value that you can be equal to. All right, so you use those when you have that little line underneath or a closed dot, or you can actually be on that value. We use a regular parenthesis when we have less than or greater than, and that is cannot be equal to. These notes are also found on Schoology, and they will be on the next slide where you could pause if you'd rather not listen and see it all written out. Sometimes the explanation helps out. Okay, the other thing about interval notation is you always need two values. Again, it kind of looks like a point. All right, the two values that you use will be separated with a comma, and around them you'll have the brackets or the parentheses. And again, you can mix and match those. And the first value is always the smallest that you can be, and the second one is always the biggest that you can be. And the order is really important that you write those in. If you have negative infinity as the biggest value, that's impossible. All right, so you always have to have the smallest and then the biggest. Let's look at an example, or a couple examples rather. All right, so if I gave you the number line that looked like this, I'm going to make mine really simple. And I had -4 and 3. And there's an open dot on 3 and a closed dot on -4. And I said it had to be between those two values. Well, the inequality, the way we would have done it prior to today is we would say, all right, my x has to be between those two values. So it has to be greater than or equal to -4, equal to because it's a closed dot, and it has to be less than 3. Now I've been doing this for years, so I know that the inequality signs are always the less than symbol, but it can get kind of confusing. Interval notation, on the other hand, is a lot simpler. You're going to think about what is the smallest and what is the biggest value we can be. Well, the smallest is -4 and the biggest is +3. Okay, now you just need to put those symbols around it. Are you going to use parentheses or brackets? Well, the -4 is a closed dot, or we can be equal to, so I would put a bracket on that side. And the 3 has an open dot, which means we cannot equal it, so I would put a closed parenthesis. I'm going to erase these lines just so you can see what this looks like. There it is. It looks like a point, but because of the way that the problem will be worded, we'll know that it doesn't represent a point. Okay, second example. Oopsies. Little bit trickier. Here's my line, my number line. I'm going to use 5, and I'm going to put a closed dot on there, and then I'm just going to point my arrow to the left. So the inequality would be, hey, I could be anything smaller than 5. So my way I would write it would be x would be less than or equal to 5. Now that one's not so bad, right? Smaller than 5, less than or equal to 5 because of the closed dot, not too bad. Interval notation is a little tricky when you start ones like this, but you'll get a lot better at it. You're first going to think, what is the smallest and what is the biggest? Well, the biggest that I can be is 5, right? I don't have anything to the right of that. So then I have to fill in that smallest side, and we don't have another number. So we have to realize that that arrow is going to be pointing us all the way to -infinity. So our smallest is -infinity. We are going to use a bracket next to the 5 because we can equal 5, and we will have a parenthesis next to the infinity because we can never equal infinity, either positive or -infinity. So if you put an infinity in there, you will have a regular parenthesis because you will never equal it. Here are those same notes written with some highlighting and such. So if you wanted to pause here to copy these down, you could. You should also be able to find your notes in Schoology. We have one more concept to talk about, and then you will have some work time. What we're going to be talking about is how we're going to use this interval notation, because we don't just use it on number lines. We're going to use it for something really useful in math that will come up a lot in our next unit, Unit 10, which is domain and range, everybody's favorite thing. But when we use interval notation, I think domain and range really starts to click with students because you're looking for the smallest and the biggest every single time. So I'm going to write it slightly differently with domain and range. And again, you can find these notes. But when we are trying to figure out domain, we are always thinking about our x values, the possible x values that our function can have. So when we're thinking about our interval notation and needing those smallest and biggest values, the smallest is really going to be the question, how far left can our graph go? And the biggest is going to be how far right the graph can go, right? If you can answer those two questions, then you've basically figured out domain. Now you're going to need those parentheses and the brackets around that, but you can think about that after you figure out how far left and right. If we are trying to figure out range, that is our y values, and our y on our graph goes up and down. So when you're writing your range in interval notation, the first one you have to think about, and this is sometimes backwards because I just said how far up and down, but you have to, in this first one, think about how low or how far down the graph can go, because down would be the smallest numbers or negative numbers. And then with our domain, it would be how far up can our graph go. And again, you'll need those brackets and parentheses around it, but once you get those two values, that's a lot simpler. Okay, I'm going to demonstrate how to do this on two examples over here in the right box. Domain, range, domain, and range. Let's just start with domain to begin with. All right, now I'm going to use a highlighter. If you happen to have a pencil, sometimes that's easier, or like a different colored pen. And hopefully you can see my little highlighter scroll back and forth. You're going to be looking for domain, how far left and how far right our graph can go. So I kind of just start by going left and right with my pencil, and I will notice, oh, look at my graph doesn't go any further than this line, right? I have to stay in that boundary. Okay, now if I'm going to the right, well, some people might say it stops here, but you'll notice there's this lovely little arrow thing. So in reality, our graph keeps going on and on and on and on. So when we're looking at domain in this first problem, the smallest, let's see, that's -4. The smallest that we can be for our domain is -4. The biggest we could be is a positive infinity because that doesn't stop going. So my domain would be -4, comma, infinity. And then we'll think about what kind of parentheses to put around there. Well, the infinity should be easy because it's always the parenthesis. Then on -4, we're going to notice that there's this open dot there. And so I know an open dot means I cannot equal that, so I'm going to use a regular parenthesis. Let's do that same thing in the second example. Okay, I'm going to look left and right and see how far left and right I can go. Well, I can't go over too far, right, to -3, -4 because I don't have part of my circle there. So left to right would be going from here, and then it does have a stopping point. So it goes from -2 to +2. So this is -2, and this is +2. So my domain would be -2 to +2. Now let's think about brackets or parentheses. It looks like those lines actually touch -2 and +2, and this is a really helpful tip, but you can basically assume it touches something, like it touches the value or equals a value, unless it is obviously an open dot. If it has an open dot or it's not exactly on the line, I think it's safe to assume that it would be touching. Okay, now with range, we do the exact same thing, just now we're going to move our pen up and down. So I'm going to think about up and down now. Now I can't go this far down, right? It doesn't exist down here, but the lowest that this graph goes is at +1. I'll write that in a second. Then you might be saying, oh, look at it stops at this +3, right? Because there's a dot there. But if we go to this side, when we're thinking up and down, it actually keeps going because we have that arrow there again. So the lowest that our graph can go would be 1, but the highest that it can go, I should write this on the other side so there's more space. The highest that it can go is infinity. It keeps going up, 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 up. So we would say 1 infinity, and I would have regular parenthesis next to the infinity, and I would put a closed parenthesis or a bracket next to the 1. You'll notice there's closed dots here, but again, even if they didn't have closed dots, I would assume that it equaled that unless it had a open dot. Second one, we're going to go up and down. Can't go down into the negative area, so this looks like the lowest it can go. And then the highest it could go would be a +4. So the lowest would be 0, the highest would be 4. So those are my values in my range, 0, 4. And again, I think I can safely assume that there would be brackets because there were not open dots. So if you look at this, it looks basically like I have 2 vertical lines and 2 horizontal lines in each of these problems. And that's a really helpful thing to put in because it's going to, close your eye to just that region. So I would recommend going left and right and up and down and drawing those lines in so it can help you figure this out. If you want to pause on this, it's the exact same information, just maybe a little bit neater, you can to copy down those notes. Otherwise, oh, here's a couple more examples we could do. Let's just do them really quickly. Okay, domain, left and right. I forgot about these. Left and right. So I would normally draw this line here and this line here and say, oh, it goes from -5 to +5. But I'm missing something crucial. I have these little arrows, right? So my domain in this example would be, I should change my color again. would be negative infinity to positive infinity. Those arrows imply that this keeps going on and on and on forever. And if you remember, this is called an absolute value function, but when we studied parabolas, if it went from negative infinity to positive infinity, this is the same as saying all real numbers, right? It's just saying anything from negative infinity to positive infinity. Then my range, I would think about how low and how high can my graph go. Well, the lowest that my graph can go is that -5. And again, some people might draw in this box or that line, but you have to remember if there are arrows, this is going to keep going. So my range would be, the smallest would be -5, and the biggest would be infinity. Okay, this would be the same thing as greater than or equal to -5. Last example, thanks for hanging in there. Left and right, furthest left I can go would be 4. And again, you might draw that line in, but you should recognize that there's an arrow that's going to keep that graph moving to the left. So my domain, this biggest it could possibly be would be 4, and the smallest, because it keeps going, would be negative infinity. So I would put the negative infinity first and the 4 second. That's a really tough one. A lot of people switch those around. Second example, or the range for this one, lowest we can go is that x-axis, which is 0, and the highest we can go, again, it doesn't stop, would be a positive infinity. So the lowest would be 0, the biggest would be infinity, so I would write 0, infinity. And there you have it. Okay, you guys again can take this information and move on to your worksheet. If you have questions, ask me the next time you see me. Have a great one.